Thank you very much for coming, all of you. It's we don't usually get crowds like this at pure crypto conferences, so this is kind of new to me. About myself, I'm a PhD student in cryptography, and of course that's something we're all quite interested in here at CCC. and in the keynote, we talked about crypto, which is so strong that even the NSA can't break it. And well, yeah, we have AES, and AES is good. But we also have a lot of talks here at CCC about crypto, which is not so strong that the NSA can't break it. We have MyFair, we have Keylock, we have the whole thing about WEP, which is kind of bad. And so I'm going to talk a little bit about new algorithms for fast encryption. So, because if your crypto sucks, then you don't get any security. Even if you do all the hard part, like making user interfaces and dealing with stupid users, then if your crypto is bad, then your system is not going to be secure. And so I'm going to talk about stream ciphers. And as opposed to a lot of the cool talks here at CCC, I'm not really going to talk about my own research, because I want to break stuff. Breaking stuff is cool. But today I'm going to talk about the ciphers which I and nobody else has been able to break. So in a sense, I'm not talking about my own research, but I'm talking more about the failure of my own research. So if you're familiar with the eStream project, then this is not going to be very much news to you. But anyway, I hope you enjoyed the talk. So here's a quick outline of my talk. I'm going to give a very quick introduction to stream ciphers first, and say something about what is it that's being used at the moment. And then I'm going to talk about the eStream project, which has been a research project financed by the European Union to develop and study new stream ciphers. And we're going to have a very quick presentation of each cipher. And so, because there are 7 different ciphers, it's going to be very quick, and so we can't go into all the details, but I'm going to at least give a little bit of an idea of what's going on. And anyway, I'm going to hang around here after the talk, so if anybody has any questions, then just by all means. Okay, so first of all, what the hell is a stream cipher? Well, it's sort of inspired by the idea of a one-time pad. And as somebody mentioned in another of the lectures, when somebody is talking about a one-time pad, they're usually wrong. So, but the basic idea is that a stream cipher is some sort of finite state machine, and you give it some initial input, and it produces a sequence of random looking key stream. And so if this was a one-time pad, then we would just be getting through randomness. And so it would be theoretically secure except against stupid users. But in the case of a stream cipher, we have instead what is basically just a cryptographic random number generator with some particular properties. So we have the key and the IV which goes in, and the key is the source of the entire security. That's the only thing which is secret. But so, just as for one-time pad, when you can only use a random stream once. And so to be able to use the same long-term key several times, you also have an initialization vector, or an IV, or a nonce, which basically ensures that even if you don't change the key, you get a new stream. And so what comes out of the stream cipher is just a sequence of random, or hopefully random looking symbols. So it can be single bits, it can be bytes, it can be 32-bit words, it can be larger chunks. And you just combine it with the data stream you want to encrypt using XOR. And of course the stream cipher is evolving deterministically, and in order for it not to be easy to just reconstruct what's going on, it has to be evolving in some kind of nonlinear way, so that you can't just solve all the equations. And so what do we mean by security? Well, the usual assumption is that the attacker has the specification and the attacker can choose the initialization values, which are public, and he also knows the key stream which is coming out. And in order to have an actual attack, we need something which breaks the cipher in some way easier than checking all the possible keys. And so, for example, if you consider a hypothetical attack machine which just brute forces a billion keys per second, and you have 2 to the 25 copies of this circuit, and you run it for a year, then you can expect to break an 8-bit key. And so to have an attack, you need something which basically costs less in money or time or whatever. And so you have two main types of attack. You have a distinguishing attack, which is that the key stream should really look like it's random. And you shouldn't be able to come up with some kind of statistical test to distinguish it, because then you can learn something about the message. And also a more serious kind of attack is if you're able to recover the internal state of the state machine. Because then you can predict future keystream output, and you can probably recover the key, and that's very bad. So I'm going to talk a bit about what is being used today, and the main example is RC4, which is it's quite old. It's from the late 80s. It was designed by Ron Rivest, and it's used pretty much everywhere. And RC4 is very nice in the sense that you can implement it in just a few lines of C, and it's very, very, very simple and very, very fast. The problem is that it's, well, by modern standards, you can't really consider it secure. At the moment, you don't have any general attack to break it, but I wouldn't trust that the NSA can't break it. I wouldn't trust that somebody who is implementing it as part of some larger program is able to use it correctly. And anyway, there are better options, so don't use RC4 in new applications. And then there's AES. You have to use AES. AES is a block cipher, so it's just a keyed permutation from 128 to 128 bits. And you have to use it in some kind of mode operation, and already there a lot of people mess up. A lot of people use CBC mode, which is good. I prefer counter mode, which basically turns AES into a stream cipher. So instead of encrypting the blocks of your message, you just encrypt the counter, and you XOR the output block with your plaintext, and you increase the counter, and you repeat. So for all practical purposes, it's a stream cipher, just like we've been discussing. And of course, AES is good, and we believe that AES is secure, and it's the standard, and everybody uses it. And it's quite reasonable. It's quite fast in software. It's not too big and not too ugly in hardware. On the other hand, there's some sort of issues about monoculture. Because as long as AES is not broken and everybody uses it, well, great. But in the unlikely event that somebody should break AES, then you die. Then nothing works anymore. So, and there's also an issue about using AES for everything, because it's very much a general purpose cipher, but if you have some sort of very specific requirement, then maybe it's not perfect. So it's nice to have some options. And what about the rest? Well, there are a lot of bad stream ciphers out there. You have the A5 ciphers used in GSM, broken. You have E0 used in Bluetooth, broken. You have MyFair, you have Keylock. People have been talking about them at CCC this year, broken. You have the EU project NESSI, which was evaluating all sorts of different cryptographic primitives. And all the stream ciphers were sort of not successful. And so the state of the art in 2004 was really quite bad. So the best example of a stream cipher in the academic literature in 2004 was probably a cipher which was called the Snow version 2. So who here has heard about Snow version 2? Raise your hands, please. Oh, okay, somebody. And who here has actually seen Snow used for anything? So there's clearly a demand for secure stream ciphers, but the problem seems to be that most of them suck. And so eStream was a research project as part of a European Network of Excellence, which included a lot of different universities and also a lot of different companies. And eStream was the encrypted stream cipher project, and the goal was really to identify new stream ciphers that might become suitable for widespread adoption. And the ciphers should provide some kind of advantage over AES, at least in one aspect. It might not, you can't expect it to be better at everything, but it should be better at something. And so eStream was not a standardization process. It was just a research project to see if we can understand better what is going on. and so it's worked mostly like the AES competition previously, like a demolition derby. So there were 34 different ciphers which were submitted, and then everybody spent the next few years trying to break each other's designs. Which is a lot of fun, because you get to break things. Yay! And there were two kinds of intended applications. One, Profile 1, which was software ciphers. And so they should be fast, efficient, output keystream at tremendously high rates, and so on. And there was Profile 2, which was for really itsy-bitsy hardware thingies with not much power, not very many gates, not very much of anything, but it should have some kind of crypto anyhow. And so a final portfolio consisting of 8 stream ciphers was selected in April this year. And the goal of my talk is really to give a very quick run through of those ciphers, and so that more people get to know about them. So first discussing the Profile 1 ciphers. The formal requirement for Profile 1 was that you should have a key length of at least 128 bits. And the IV, the nonce, should be either 64 or 128 bits. And so the portfolio consists of 4 different ciphers. There's HC 128, there's Rabbit, there's Salsa 20, and there's Sosumanuk. And I believe actually one of the designers of Sosumanuk might be here, although I don't see him. But oh well. So moving right along. HC 128 is named after the author, Hong Yun Woo. And it's got a 128-bit key length and a 128-bit IV. The state is quite large, because it consists basically of 2 large registers. And it outputs 32-bit values. And for a single key and IV, you can produce 2 to the 64 bits, which should be enough for anybody. And it's expected to have 128-bit security. And so the basic update parts of the cipher is attempted illustrated here. So the basic idea is that the cipher starts with one of the registers at position 0, and then it updates the value of that position using a nonlinear function g and 3 other cells. And then it uses that cell, which is then a 32-bit word, and combines it with some other 32-bit values that it gets from the other array. And it uses It uses basically part of its state as the index and SBOX lookup. And so you go through the state array, updating it at each position, and using the other array as the SBOX, and then you switch. So you go through the second array and update all the values while using the first array as the SBOX, and then you repeat. So I think this is the only. Software cipher which actually uses an SBOX. So a surprising thing here is that most of the ciphers are based on sequences of add, XOR, and rotate. And SBOXes don't seem to be used very much, at least not in the profile ciphers. So some notes about HC. It's the eStream cipher that resembles RC4 the most, in the sense that it's based on arrays which are being permuted and updated. And there aren't any known attacks against it. So there has been some discussion about cache timing, because 4 kilobytes of state is really quite large, and you have to do lookups in the state that more or less random. And there might be some issues there with things being swapped in and out of cache. But anyhow, when you are encrypting very long messages, it becomes very fast, because the actual state update function is very simple. It's just some rotation and some addition. But on the other hand, it basically takes ages to fill up 4 kilobytes of state with something which is sufficiently random from just the seed of the key and the IV. So if you're trying to encrypt short packets, then just forget it. But if you want to encrypt huge amounts of data, then HC is pretty good. And so there's also variant HC256, which supports longer keys. Moving on, there's Rabbit. Rabbit was designed by the Danish company Cryptico. It's got a 128-bit key length and a 64-bit IV. The state consists of, and so the state is much smaller than the HC. It consists of 16 32-bit words, and as well as 1 carry bit. And at each step, you extract 128 bits from that state. And you can extract 2 to the 64 of these blocks for a given key and IV. And Rabbit looks basically like this. So it's very, very nice and symmetric. So each value of x is updated based on the 2 previous values in the circle, as well as the associated counter. And this is done in a nonlinear way using addition, XOR, rotate. And the counters are being updated, or they're being incremented with some constant value at every step. And also, whenever one of the counters overflow, there's a carry bit which goes into the next counter. And so at each step, you use all the x's to extract the 128-bit block. So each part of that block is essentially the XOR of two of the x's. And so, as you can expect, this is quite fast in software, because it's all based on simple word operations. Rabbit was first published in early 2003, and as it was designed by a private company, it was the only portfolio cipher in eStream which had patent issues, because Cryptico were trying to patent it. but it's always been free for non-commercial use, and it was also announced in this summer that the cipher was released into the public domain. So this is not a problem anymore. And Rabbit is also I think the cipher which has come the furthest towards any kind of standardization. It's described in RFC 4503, and it's about the same speed as AES for the short 40 byte packets, but it's very fast in long streams. So at least one of the highly optimized implementations is running at 2 cycles per byte on, I don't remember which platform, but this is quite efficient. AES is running at like 15, 20, again, depending on the platform. So, moving along, we got Salsa 20. And Salsa 20 was designed by DJB, and I'm sure most of you know who DJB is. He has a bit of a reputation. And I've mostly met DJB in the context of pure academic cryptography, and in that field he is a big expert, really. And if he's talking about crypto, then you should probably listen. If he's talking about various other things, then maybe not so much. I don't know. And this also goes for what was said about DNS curve and curve 25519, which curve 25519 is DJB's elliptic curve implementation, and it was published in a research paper a few years back. And from a cryptographic point of view, it's clearly very good. From a practical point of view, with respect to patents and standardization and politics and all that, then maybe not so good. But at least the crypto seems to be good. So to go back to Salsa 20, it's got a 256-bit key length, which is huge, and the IV is 64 bits. And the state consists of a 4x4 matrix of 32-bit words, so it's 512 bits. And what is special about Salsa 20 is that whenever it outputs keystream, it actually outputs the entire state. And it's expected to have 256 bits of security. So here's Salsa 20. The basic idea is that you have an operation which is called quarter round, and quarter round takes in 4 input words, and it uses a combination of addition, XOR, rotate to mix them all together. And so to perform 2 rounds of Salsa 20, you first apply quarter round to each of the rows in the matrix with different indexing as indicated by the red. And then you do the same thing for the columns. So that everything is being just smeared together, but first across and then down. And the quarter round function is, as I said, just a simple addition, rotate left, XOR. And what Salsa 20 does is that it does a number of these rounds. Well, first you fill up the matrix with the key, the IV, a block counter, and some predefined constants. And then you run this for a number of rounds. And then you XOR the state that you get with the initial state, and then you output it. And to encrypt the next block, you just increase the block counter and do it all again. And so this is, I think, a very clean and nice design. And you have a lot of tunable parameters like the number of rounds. And so Salsa 20X has X rounds, and the full version, which was proposed by DGB, had 20 rounds. But seeing that the best attack that we know about is for only 8 rounds, the stream decided that Salsa 2012 was probably a good compromise. And again, it's slightly faster than AES on short packets, and it's quite fast for long streams. There's also a variation which is called Cha-Cha, which was proposed early this year, and it's basically, we think that it's slightly more secure because it modifies the quarter round function in a way that might be slightly better. But again, it's highly experimental. So, and finally, we have Susmanuk. And Susmanuk apparently means snow snake in the Cree language. And that makes a certain amount of sense, as we will see. And it supports a key length of 128 to 256 bits. But the only security guarantee given by the authors is that it should at least give 128 bits of security. The IV is also 128 bits, and the state is very small. It's only 384 bits. And the amount of stream you can generate from a single key in IV, I couldn't find it in the spec, so I don't know. It might be specified somewhere, but I really couldn't find it. And so this is the basic structure of Susmanuk. You have a 320-bit linear feedback shift register, which just cycles. And then you have what they call a state machine down here, which contains 64 bits in R1 and R2. And then everything is linked together and interacts somehow. And the output is fed through the serpent round function. And so, of course, the reason it's called snow snake is because it reuses parts of both snow and the block cipher serpent. And you could probably have some discussion about that, because on one hand, reusing previous components means that people have looked at them before and they aren't completely new and you have some kind of idea what's going on. On the other hand, my personal opinion is that this is kind of a mess, and I think it's quite hard to analyze Susmanuk in a meaningful way because the structure is so complicated and everything is going everywhere. And somebody called it the Franken cipher because it was basically bolted together of parts of dead ciphers. But and so the best known attack on Susmanuk is about 2 to 224 steps. So you probably shouldn't be using 256-bit keys and expect full security, but it's very far from 2 to the 128, so for 128-bit keys it should certainly be secure. And the performance is also quite good. So moving on to the hardware ciphers, Profile 2. So Profile 2 is basically crypto for crappy small embedded devices without anything. And 80-bit, the keys should be at least 80 bits, and 80-bit keys is probably good enough for short-term ephemeral secrecy. As I estimated at the beginning of my talk, if you can test 1 billion keys per second and you have 33 million circuits and you run for a year, then you break it. So it's probably good enough. It's certainly better than key lock and all this stuff that people are actually using. And 80 bits is also roughly equivalent to 1024-bit RSA. And The hardware ciphers are mostly bit-oriented, so instead of operating on machine words, they're usually just moving single bits around at a time. And you will also see that you have a lot of shift registers. And we have 3 ciphers, grain, Mickey, and trivium. And moving on to grain, I have no idea where they got the name from. But that's a problem in general with things. You have to think of a name. Okay, somebody has a bright idea. Ooh, name. And the key length is 80 bits. The IV is 64 bits. And now when you look at the state, it's just 2 80-bit registers. So 160 bits. And comparing to the software ciphers, that is, of course, very small. Again, I don't think the amount of keystream is specified anywhere. But it outputs 1 bit at a time. But that bit, but the state doesn't depend on the 16 last bits. So if you unroll the loop, you can produce 16 bits in 1 clock cycle at the cost of a slightly larger implementation. And the security is thought to be 79 bits, because there is a very simple way to check 2 keys at once. So if you're trying to brute force the key, then you can do it twice as fast. And so this is the basic structure of grain. You have an 80-bit linear feedback shift register, which is completely linear. And it produces very statistically nice randomness. But on the other hand, it's linear. But then it's linked to an 80-bit nonlinear register, which is evolving more unpredictably in a sense. It's much harder to analyze how the state is evolving. And so at each step, you take 5 bits from the state and put it through a nonlinear a Boolean function. And then you XOR it with 7 more bits from the state and output it. And so, as I said, you can unroll this so that you get 16 bits at a time instead. And grain is the most compact of the hardware ciphers. It can be implemented in, I think, about 1,300 NAND gates. I think that's quite small. I don't know all that much about hardware implementation. And the fact that you can unroll the loop at the cost of a larger implementation means that you have a trade-off between size, power, speed, and you can make different choices. On the other hand, the security of the cipher is extremely tight, and you have an attack on the initialization procedure, which is about the same as brute force. There's a sliding property, which means that you're able to check 2 keys at once when you are doing a brute force attack. And you can also make a kind of time memory trade-off, which is, I think, the only part of my own research which appears in this talk, which means that if, for some reason, you have to crack 1 billion different grain keys, and you have access to huge theoretical amounts of data for each key, then you can probably do it faster than just brute forcing all the keys. Which may or may not be useful. I don't think it's very useful, but at least it's something. And there's also a 128-bit version of grain, which basically replaces the registers with 128-bit registers instead of 80. Then there's Mickey. Mickey is one of these very cute abbreviations. It stands for Mutually Irregular Clocking Keystream Generator. And you have 80 bit of key length, 80 bit of IV, 200 bits of state, so it's a bit larger than grain. And you can output 2 to the 40 bits for 2 to the 40 different IVs before you have to change keys. Mickey looks sort of like this. Again, you have 2 different registers which are coupled together. But in this case, the coupling is a bit more complicated. So at each step, you get a control bit which decides what kind of feedback you get in the linear register. And similarly, there's a control bit which chooses between 2 different nonlinear feedbacks. And this construction means that you can't unroll Mickey the same way you could with grain, because it's tied to, there are too many dependencies. And so Mickey is, I think, the slowest and largest of the hardware ciphers, but again, the security margin may be somewhat better. There aren't as many near-miss attacks on Mickey as on the others. There might be some concern that you get side channel problems because of the irregular clocking, but that depends on how you implement it, I guess. And there, as before, there's a variant which supports longer keys. And the final portfolio cipher is Trivium. And the name refers both to the structure of the cipher, which is divided in 3 similar parts, and also because the design is so simple that maybe somebody someday can write a paper with the title 3 Trivial Attacks on Trivium. That would be nice. And so the key and IV are both 80 bits. The state is quite a bit larger than the other 2. And this time you can unroll the output for 64 bits. So instead of outputting 1 bit at a time, you can implement it as a larger circuit and output 64 bits at a time. And so this is the only cipher I didn't draw my own figure for, because this was the figure by Christophe de Canier in the original paper, and it's so nice that I just keep it. So the basic idea is that you have 3 registers, and at each step you take a few bits out of some specific positions, and so these 3 registers are all linked together and modify each other. And the only nonlinearity in Trivium are these 3 AND gates, here, there, and there. Everything else is just linear. And also the output function is just a simple XOR of 6 different state bits. So this is the fastest cipher in Profile 2, at least if you unroll the loop. And it's also fast in software on some architectures, because you can unroll it so it works on 32 bits or 64-bit chunks at a time, and then you can implement the logic without too many complications. And because it's so simple, everybody's been trying to break it, and nobody's quite succeeded. There are some guess-indeterminate attacks which break it by, I think, complexity 2 to the 83 instead of 2 to the 80. And there's also a quite new paper which tries to attack the initialization, and it works for almost all of the initialization they think. So again, the margin of security is maybe not very large. And the attack by Maximov and Birkov also means that you can't really use a longer key because the security doesn't increase. And so to the final cipher, because there used to be 4 hardware ciphers, except that somebody broke the last one. And this is sort of the danger of using experimental ciphers. Sometimes they break. And but it should be said that FCSRH was probably also the least understood cipher in the hardware category. It was using some kind of weird nonlinear registers that hadn't really been studied very much. And so this attack was actually quite good. It breaks the cipher more or less in real time. So, which is bad. And so there's a question of how much confidence we should have in these new experimental ciphers. And of course it's true that attacks never get worse, they only get better. So the fact that you have, especially in the hardware category, some ciphers where you have some pretty near-miss attacks means that the margin of security is not all that big. And these are also quite new designs, and so AES is a much older cipher, and so there's more reason to believe that it's secure. But and there's a question of new attacks, like cube attacks was invented, or at least made public at Crypto this summer, and nobody's had it on the radar, and we don't know really how it applies yet. So there's a bit of a warning here that this is still quite new. On the other hand, this is the best. The research community has been working on stream ciphers quite focused for the last 4 years. And these are the best ciphers we were able to come up with. So if all of them are broken, then it means that nobody has a clue. How is the time? Oh, plenty. So I'm about to wrap up. And so the next big thing, of course, is the NIST hash function competition. Because NIST wants to find a new hash function standard. And so they've announced a contest similarly to the AES process and to eStream, in that everybody can submit a design, and then there's going to be a competition to see which will become the standard. And the way I see it, what we know about hash functions today is maybe 10 years behind the understanding of ciphers. And like sort of like DNS, everything breaks if you have a bad hash function. If you use MD5, then your crypto may be great, but it just isn't secure. So it's going to be very interesting to see what will come out of this. And there seems to be an exponential number of submissions in the AES process. I think there was maybe about 10 proposals. For eStream, there was 34. And in this case, they actually got 64 different submissions for the call for primitives. And already a lot of them have been broken, but there are still plenty left. And this competition is going to be going on for another 3.5 years. So there's plenty of time. It's an open process. Everybody can contribute implementations, analysis, whatever. And so here's my summary. The eStream project has identified 7 new promising stream ciphers, and they have different performance trade-offs, and all of them are better than AES in some respect. Either they are faster, they are smaller, they are whatever. And I think also the results of the eStream process reflects a certain kind of consensus in the academic crypto community. Because there was an anonymous poll at Fast Software Encryption in February, and which tried to rank the confidence in the different candidates by cryptographers, and it corresponded to the final portfolio. So this was the best we were able to come up with, but of course, something may be broken in the future, and if you're in doubt, AES, preferably in counter mode, if you ask me, is still the safest choice. Thank you. Any questions? In the back?
In the initial call to eStream, they were looking for authenticated encryption too. But already in phase 2, nobody of the authenticated stream ciphers survived. When I want to apply encryption and integrity, what should I use? AES Encounter and AES CVC Mag? a combination with the stream cipher. The main problem is low latency. So encryption is fine, but encryption without integrity doesn't much make sense.
Yeah. Yeah. So the question was what you should do if you want, or if you need integrity as well as encryption, and I completely agree. A lot of things stop working if you don't also use some kind of integrity checking with your crypto, and and the best thing to do is to use some kind of secure encryption mechanism, whether that be AES or one of the stream ciphers or something different, together with the MAC. And there are several secure MAC constructions which can be used, and you should just look at the performance of the different options and pick the one which is the fastest. Any other questions? No? Well, I'll be around afterwards, so feel free to approach me if you have any other questions. Thank you.